So what happens when a wave is reflected off the wall and meets its...
Can't hear you, Mr. Drew.
Oh,
I'm sorry, I can't hear you.
dear me.
Right, here I have a signal generator which is producing a very crisp sound at roughly 2000 Hertz. Sound is produced from this speaker, is hitting the wall and reflecting back off the wall. Here we've got a microphone and we're going to measure the intensity of the sound. I'm sure you all heard that very clearly, so I'll just repeat that. Sound wave going towards the wall, reflecting off the wall, coming back, and we're going to measure the intensity of sound by looking at the height of this trace on the oscilloscope. Now you would expect the height of the trace to get bigger and bigger as we get closer to the sound wave. So let's see if that actually happens. Now I hope what you saw then, and I'll show you again with close-up, is that as we get closer, the sound actually gets weaker, and then it gets louder again, and then it gets weaker again. Let's watch that one more time. So if we focus on the oscilloscope now, we'll bring it closer, it's getting smaller, getting bigger, and getting smaller. Now what I want to do is I want to measure the distance between two minimum points. So I will do that now. Let's get one minimum, this is about there, make a note of that. Okay, and it's about 9 centimeters. Okay.
I'm going to use Walter Fenn's animation on the internet to demonstrate how standing waves are set up in a string which is fixed at one end. We can start the wave in the string like this, and you can see that the string starts to vibrate as a normal progressive wave travelling to the right down the wave. When the wave reaches the fixed end, it will reflect. Reflections at a fixed end are pi over 2 out of phase with the wave coming in, and this is quite important. So what will happen as the wave reaches the fixed end, it will reflect, and this will produce for us a blue wave, so we can see this quite clearly. So now we have two progressive waves travelling down the string, the red one moving to the right and the blue one moving to the left. Of course, what is going to happen is that these two waves are going to superpose with each other and produce a resultant effect. And we can show that by clicking this box here, and we'll see the resultant wave in black. What you might notice about this, which is really interesting, is that although you can see clearly the red wave is moving to the right and the blue wave is moving to the left, you can see that the black resultant wave doesn't actually seem to be moving anywhere at all. There are points of maximum amplitude which seem to be vibrating simply up and down, but there are also points on the wave which are not vibrating at all. So let's just stop that in this position here. The end, of course, here where the cursor is fixed, so can't vibrate. We call this point a node. But you'll see that there are several other nodes moving down the wave. You will also see points of maximum vibration here, here, and here, so on. These are known as antinodes. So if we just get this going again, you will see that the antinodes are points of maximum vibration. Let's try and figure out how this happens. Let's stop it here. Now if you look here, you can see that the red wave, the wave moving to the right, and the blue wave, the wave moving to the left, are both sitting on top of each other. So the resultant wave here is the height of the red wave plus the blue wave, which is almost double the amplitude of the progressive wave. So we get this amplitude here. You can see in this position here, this node here, that both the red and the blue waves have zero amplitude, so the resultant wave will have 0 amplitude. To watch us carefully, what we can do now is make the wave progress in just single steps. I'm going to choose an 1/8 of a period, but I can choose different times if I wish. If I just resume it so the wave progresses. Now let me keep the cursor, watch this point here in the middle. So let's go back to this point here. Now you can see it's still a node, so if we look at the red wave, it has a height there, above the line, and the blue wave has the same distance below the line. So when we add them up, one is positive, one is negative by the same amount, so again they cancel, so hence the node remains. If we move it forward another 1/8 of a period, there's the same node. Look, that's at its maximum, the blue wave's at its minimum. Together they still cancel, and in fact if we do it again, you can see the same happens again, and again, and again. So the node remains in the same place. Let's now look at an antinode here, for example, this antinode here. Look, this wave and this wave are both positive, so they double in height to give you this position here. Moving it on, you can see that the string has come back down there. Moving it on, you can see that they're both now negative, so we double the depth of the wave. Moving it on a bit more, they're on top of each other, so we have our antinode. So if we now get this actually moving again, and now hopefully you'll understand this a little bit better, as the two waves move through each other, we have points of maximum vibration and points of minimum vibration. What I want to do now is compare a travelling wave or a progressive wave with a standing wave. This is a fairly common question on an IB physics paper. So what we'll do, we'll get our incident wave showing and we'll get it moving. There you go, so there is a normal progressive wave. Firstly, let us consider the energy of the wave. Well, the energy is clearly being transferred from left to right. But if we now look at the standing wave, you can see that as there's vibration, well, there must be energy associated with the wave, but it's clearly not moving anywhere. Now let's consider the amplitude of the wave. If we go back to the progressive wave, you can see that all points along the string will have the same amplitude. There's the maximum, and as you can see, this maximum amplitude is progressing along the wave. So every point, doesn't matter if it's there at the moment, it's at a minimum, now it's at a maximum. But if we look at the standing wave, you will see that this point here has maximum amplitude. This point here, well, it's not vibrating at all, so has no amplitude, and at some point in between it has some amplitude in between. So in this case the amplitude depends on the position in the wave. Now if we consider the phase, you can see that the phase that the wave is in depends on the time that has passed. So ultimately all waves will go through a cycle from 0 to 2 pi. In the standing wave this is quite different. If we go between these two nodes here, you can see all the particles in the wave are now moving down together, they're moving up together, and they're moving down together. But if you compare this segment of the wave with this segment of the wave, you'll see that the one on the left here is moving up while this one is moving down, and this one is moving up while this one is moving down. So if you look at neighbouring segments, you will see that they're moving in opposite directions. So there are only really two phases associated with the wave. The waves in neighbouring segments are pi out of phase with each other. Now if we consider the frequency of the wave, you will see that all particles in the progressive wave vibrate at the same frequency, and similarly for the standing wave, all particles vibrate at the same frequency as the waves which are superposing to produce the standing wave. Now let's consider the wavelength. The wavelength of the progressive wave, let's just get rid of the standing wave there. Let's just stop the wave there. We know that the wavelength is from any point in a wave, let's choose there, to a point in the next wave which is at the same phase. So if we start there, go up there, down there, there. So the distance from there to there is one wavelength. We could choose to start there, so that is one wavelength. Or we could start there, and that is one wavelength. Or in fact, we could start anywhere in the wave and move to the next wave to a point which is in the same phase. However, with the standing wave, this is quite different. If we have the standing wave in like this, you can see the distance from there to there is actually one wavelength of the incident wave, but you can actually see that that wavelength is the distance from one node, not to the next node, but to the next consecutive node. So the distance from one node to the second node is one wavelength. So the node to node distance in a standing wave is half a wavelength. So if we bring in our reflected wave again, try and make sure that when you're asked to compare a standing wave with a progressive wave, you mention all the things we mentioned there. You need to mention the energy, the amplitude, the frequency, the wavelength, and the phase. So overall, in a progressive wave, the wave pattern moves, but of course it's stationary for a standing wave.
It's me again. This is the data we just took. The frequency of the sound was arbitrarily about 2 kilohertz. I'm sure it may be somewhere a little bit plus or minus from that. Now the node to node distance, now the node is a point in the wave of minimum amplitude. So the node to node distance, which is from a low point to the next low point, is 9 centimeters. Now if you look up a little bit of physics, you'll be able to realize that we can work out the speed of sound. We need to multiply the frequency by the wavelength, and the node to node distance is very simply related to the wavelength, which you can now look up.